Okay, so in this video we're going to take a look at electric potential for point charges. And the first thing I want to mention is that the variable for potential is the letter V. I'm not sure why they chose the letter V, but that's what it is. And also remember that I suggest you put the serif on your V so that there's no possibility of confusing potential with volume or velocity. Now, the thing to remember about potential is that it's only the possibility that energy will exist. And the energy will only exist if a charge is placed in the region of space where you are looking at the potential. So in short, potential is not energy. Potential is not energy. It's only the possibility of energy. Now, if you recall with electric fields, we had E was defined by force over charge, and that was going to be a test charge. Well, we're going to be doing something similar with potential, and we're going to say that potential is defined by the electric energy, the electric potential energy, divided by the test charge. Oftentimes, we write the electric field F is equal to F over Q. We'll write that as F is equal to QE. And oftentimes you will see that electric potential energy is written as Q times V. Now, there's something we need to be really careful with when it comes to potential. Potential V is measured in volts. It has the unit of a volt, and a volt is 1 joule per coulomb. There's another term, another unit called the electron volt, EV, and the electron volt has nothing to do with potential. Because the electron volt is a unit of energy, it has a value of 1.6 times 10 to the minus 19 joules. And we'll talk later about how we get the electron volt. So now that we have a definition for potential, let's take a look at the electric potential for a point charge. We know that the potential is defined by U over Q, Q naught. And with point charges, we know that the potential energy is going to be K, Q over R. So this was capital Q is the source charge, little q is our test charge, and R is the separation distance between them. And we divide that by Q naught. So the test charge we always write as Q naught. So what happens? Q naught cancels out, and we end up with the potential V is equal to KQ over R. And that Q is the source charge. Now when it comes to electric potential, it's helpful to remember that the size of the charge being placed makes no difference. That is the test charge. It's similar to gravitational potential, where gravitational potential we would say V sub g. That would be defined by gravitational potential energy divided by mass. So that would be mgh divided by m. The m's cancel out, and we end up with just g times h. So gravitational potential doesn't have anything to do with the mass of the object being placed. It has everything to do with the mass of the source, which in this case, g, the gravitational field, the source for that is the Earth. So only the mass of the Earth would matter. Well, when we're talking about electric potential, only the charge on our source charge is going to matter. So that's another important point, and that is that source charges determine fields and potentials. Test charges contribute to create force from field and energy from potentials. So for example, if, just to help you wrap your head around this, we have the Earth here. So here's our Earth, and we're looking at this point in space somewhere near the surface but above it. And at this point P, I want to know a couple of things. One, does a force exist? Two, does a field exist? Three, does potential energy exist? And then four, does gravitational potential exist? And so at this point above the Earth, is there a force located at this point? Absolutely not. So there's no force. But yes, we do have a field, and that field takes on a value of G, which is 9.8 newtons per kilogram. Does energy exist at this point in space, at point P? No, we do not have any gravitational potential energy because we don't have that second object that's placed there. However, yes, we do have gravitational potential, and that's going to be equal to G times H. We can do the same thing for charges and electricity. If we have a source charge right here, and we're looking at this point P right there, we're going to ask all four of these questions once again. So one, does a force exist? And to that you would say no. You need a test charge to create a force. Two, does a field exist? And to that we would have an emphatic yes. And the field is just going to be equal to kq over r squared, where q is this, the source charge. Three, is there electric potential energy at that point in space? And to that we would say no, because we still need a test charge. But four, do we have an electric potential? And the answer to that is yes. V is equal to K times the source charge over R, where R is the distance between the source charge and the point in question. So the big idea here is that force and fields go together. One is used whenever you don't have a test charge. And then we have energy and potential. They go together. And potential is what you use when you don't have the test charge. So if you want to take a force perspective in solving a problem, you're going to use forces or fields. And if you want to use an energy perspective to solve a problem, then you're going to use energy and potential. Okay, so how do we find the potential of multiple point charges? Well, basically we're going to use superposition, and I use that term very loosely because superposition is how we add up vectors from multiple charges, and we're dealing with scalar quantities here, and so it's not technically superposition, but in effect, we're going to be using superposition of each charge at the location in question, except we're going to ignore all the angles. And so whatever the value for the potential is, as we get it from V is equal to KQ over R, we just add it up. You're never going to see sine and cosine. You're not going to see the trig associated with this. So we ignore the angles. Okay, so when we do this, keep in mind that the potential of negative charges is negative. The potential of positive charges is positive. It's also helpful to keep in mind that the potential at a point in space may be zero. And not to add any confusion to this, but just because the potential adds up to zero doesn't mean the electric field is zero. So the electric field may not be equal to zero, but the potential is equal to zero. And let me give you an example of that. If we take a dipole, which is two oppositely charged but equal magnitude charges, and if we take a look at this line of symmetry right down the middle, let's just go right here at this middle point, and let's just look at this point right here. If I want to know what the potential, the total potential at that point, let's call that point P. So the potential at P, what is that equal to? Then we're going to use KQ over R for each one of these points. So the potential at point P is equal to KQ positive over R plus KQ negative over R. Now, the R from this point to this point is the same as the R from the positive to that point. Okay, so both of those R's are equal. Both of these charges, these source charges, are equal in magnitude but opposite in sign. So what happens is the potential is equal to zero because both of these come up to the same magnitude number but opposite signs. And that's going to be true for anywhere along this midline. The only thing that's changing based on where you are on that midline is the location R, or I should say the distance, how far away you are from the charge. Okay, now, the electric field, on the other hand, that, because it's a vector, does not add to zero. Because if you look at any point, let's say look at this point, then the electric field due to the positive charge points up and to the right. The negative field due to the negative charge, or the electric field due to the negative charge, points down and to the right. And so you have these vertical components, EY for the positive charge and EY for the negative charge. Those two cancel out, but you still have an EX for each of those, so the net electric field due to the point charges anywhere along that line is pointing to the right. So E is a non-zero value. Now, there's another term that we use when dealing with potential which can possibly cause some confusion if we're not careful, and that is potential difference. Now, you could probably figure out what that means, but basically it measures how much the potential changes between 2 points in space. So if I put a source charge right here, and I'll make that positive, and I look at this point in space right here, and this point in space right here, we'll say that this is point A, this is point B. We'll call this Q1. Okay, I can calculate the potential at A. That's just going to be equal to KQ1 over RA, and the potential at B is equal to KQ2 over RB. So if I want the potential difference, mathematically all we're saying is that the potential difference is delta V, which is equal to VB minus VA if I'm going from the location A to the location B, if I'm moving outwards. All right, now let's just say, for example, that I calculate the potential at point A to be 10 volts. I'm just making up this number. So VA is equal to 10, VB is equal to 3 volts. Then when I calculate the potential difference, I should get 3 minus 10 is equal to 7 volts, negative 7 volts. Now we have to be careful with what that actually means, because all that negative sign is telling us is that as we went from location A to location B, there was a loss of 7 volts of potential. And if you had actually placed an object in there as you went from A to B, a charge from A to B, then what that would mean is that there is a loss of potential energy which was proportionate to that minus 7 as you went from A to B. Now, on the flip side of things, it's possible that we were going from B to A. And if we're going to go from B to A, then delta V is no longer B minus A, but it's going to be the potential at A minus the potential at B. So delta V in that case is going to be equal to 10 minus 3, which is a plus 7 volts. And what that's telling us is that there was an increase in the potential energy as we went from B to A. Now keep in mind, my description of loss and gain of energy was all dependent upon a positive test charge. If you use a negative test charge, then everything is opposite. As I take a negative charge from A to B, even though there is a loss in potential, there was an increase in potential energy because the particle is naturally going to want to be attracted towards Q1. So you're actually adding energy into the system when you go from high potential to low potential with a negative test charge. And in the next video, we're going to talk more about the sign for potential. So we'll see that more in a little bit later. So why do we bother using potential? It seems like there's a lot of quirky things that we have to pay attention to. And the answer is pretty short and sweet. It's easier to measure. Electric fields are difficult to measure, but electric potentials are easy to measure, and for that we just use a voltmeter. And so to help explain how a voltmeter works a little bit more, I am going to go to a simulation to explain it. But the basic idea behind a voltmeter is that you have a red wire and a black wire, or probes. And whenever you use a voltmeter, it's always red with respect to black. Now what that means is we're asking, what is the potential at the red wire if the black wire is 0 volts? What is the potential of the red wire if the black wire is 0 volts? Or, to say it another way, how many more volts do I have at the red wire compared to the black wire? So let's take a look at the simulation now. Okay, so I've set up a really basic circuit. I've put in 3 resistors. I have a battery which is set to 100 volts. And so in order to determine the voltage of the battery, I will place my red wire on the positive side of the battery, and I'll place the black wire on the negative side of the battery. And you can see that it's reading at 100 volts. So that means the red wire has 100 more volts of potential compared to the black wire. Now, if I go the other way around, you should expect that the voltmeter reading would be what? If you said it would be a negative 100 volts, then you would be absolutely correct. Okay, so again, we're measuring the voltage of the red wire compared to the voltage of the black wire. So as you go around a circuit, again, this is review from last year. This should not be the first time you're seeing this. We should have the potential of this part of our circuit being the exact same potential as the battery, potential difference as the battery. And so that would be 100 volts because no energy has been lost passing through a light bulb, resistor, or electric motor at this point in space. However, if I pass over a resistor and these three resistors are equal values, then I should lose 1/3 of my energy because each resistor is going to take the same amount of energy. And so if it's at 100 volts, I would expect it to be at 67 volts. Right? And here we have a 67 volt difference between 0, or the negative side of our battery, and that first resistor, or just after that first resistor. All right. Now, that means we had a 33 volt drop. Okay, now how do I get that 33 volt drop? Because the high side is 100 volts, the low side is 67 volts, my voltmeter is reading a negative 33 volts. Okay, so what is it going to be if I'm measuring the voltage drop across the second resistor? The voltage drop should once again be 33 volts, which it is. But if I go across the two resistors, it's 67 volts. It's a negative 67. It's a drop. Okay, so that's what it is. It's always red with respect to black. Even though this is a 100 volt circuit, in terms of the voltage reading you get from your meter, it's always going to be as though the black wire is at 0 volts, and we want to know what is the voltage at the red wire. Because ultimately, the only thing that matters when it comes to electricity is the potential difference between the 2 points that you're interested in. And this is how linemen who work on the high voltage power lines that crisscross our country, the voltage is something like 100,000 volts, and they're literally connected to and hanging from these wires. They're touching them, and yet they're not getting electrocuted. Birds sitting on a telephone pole, on the wires up on the poles, why don't they get electrocuted? And that's because the potential difference between their 2 feet is 0. That would be like this. So we have this, let's just say this is a high power line, right? So a bird sitting on it, his left foot is sitting right here, and his right foot is sitting right here. So what's the voltage between the 2 feet? It's 0 volts. Okay, but if that bird were somehow able to straddle 2 different wires, then we would end up with something that looks like that, and the bird would get electrocuted.